Welcome to this lecture on space mission for detection and characterization of exoplanets. I didn't choose the title nor anything. In this presentation, I'm not an expert of space telescopes, so if you know something I don't know, just shout at me, tell me I'm wrong. Everyone present himself, so I just put a slide here to present myself. So that's me, there's a bunch of stuff here. The nice thing is that I'm currently a research fellow at UCL, where I work on exoplanet atmospheres. I technically got a visiting position to Tokyo University, but I never went. Naoji, it's the same-ish. But as of September 2022, I'll be ESA Research Fellow at the Space Telescope Institute to work on James Webb and the characterization of exoplanet atmospheres. So just down below are the three things I'm very interested in. The first one is atmospheric codes, so I do write codes. So modeling and things like that. This is what we call an atmospheric retrieval code. This is a model I've developed. And here it's a population analysis tool to analyze exoplanet atmospheres, but like not one, but as populations, so like a number of atmospheres. Here, those are the four babies I play with. So there is JWST, Ariel, Spitzer, and James Webb. I'm going to talk about each of them. And I'm interested in developing atmospheric codes to work with data of those telescopes and understand planetary systems in general. As you can see, I'm not a geophysicist nor a meteorite expert, so I'm very glad to be here today. Then I can learn a lot more about meteorites, and this is now the extent of my knowledge on meteorites. So yeah, as I say, if you have something else that I didn't mention and that you're more expert than me, just please don't hesitate to speak up. I've started with a survey because I really liked yesterday the quiz that was given, so I've done one. Go ahead, have fun. Okay, all good. So I'm going to continue now. Any objection? No? Okay. Plan. Just before the plan, I'd like to say that, it's 3 p.m. We just got lunch, so we're all very tired. I'm tired. So I will ask you to interact with me. If you have any question on one slide, just please stop me, ask the question. Don't wait till the end, because I'm not going to answer questions after this talk. I'm just going to go sleep, right? No, if you don't want to answer the question during the talk, it's fine, but please interrupt me if you have anything specific. I'm not going to move too much, because I'm not allowed to do so, but usually I do move. Okay, in terms of plan, we start with detection of exoplanets, then we'll go to characterization of exoplanets and atmospheres, and then we'll talk a little bit about next generation space telescopes. So first, detection of exoplanets. Did you know that the first detection of an exoplanet is actually not by Michel Mayer and Didier Queloz, but this is by those two guys here in 1992 around a pulsar and not around a normal star. I don't know if we can call a pulsar a normal star or not. So it was in 1992, and then Mayer and Queloz got the Nobel Prize for 51 PEG-B. So it was a discovery in 1995. Oh yes, I forgot to mention, but they found those two planets based on the timing of the pulsar pulsations, which was variating, and a pulsar doesn't variate. So they found out that there was two planets orbiting this one. For Mayer and Queloz, do you know which technique they used? Someone knows? Radial velocity, yes. Is anyone aware of what radial velocity is? Okay, cool. I'll talk about it. Then in 2000, HD209 was discovered through another technique, which is called transit. Is anyone aware of what a transit is? Oh, so you know transit, yes? Do you want to tell us?
The variation of the luminosity of a star when the planets transit around the star?
Absolutely. Do you want to come to the lecture? There's actually 2 discoveries in 2000 by 2 different independent teams, and those are the light curves that we can get. So this is one first transit, and this is a second transit that was observed by Charbonneau in 2000, and Henry also observed a partial transit. So this is a curve that shows the cumulative number of detections in the last, 40 years. This is separated in the different techniques, so radial velocity, transit, and there's a number of other techniques I'm not going to talk about because we don't really detect a lot of planets this way anymore. But do you know what happened in 2009 that basically jumped this number of detection from basically, 400 up to 5,000 now? Yes? Yeah, and you don't have to raise the hand, just shout the answer, it's fine. Yeah, so now we know more than 4,800 planets. They have been detected by various detection methods. The main 2 are the transit and the radial velocity. The cool thing about those 2 methods is they are very complementary. So with transit, we can get constraint on the radius of the planet, and with radial velocity, we can get mass. The revolution here in 2009 was Kepler. There was a number of other telescopes involved, so COROT and TESS are space telescopes. Then Gaia is also a space telescope. Do you know what Gaia do? Astrometry? No? Okay, I'll talk about it a little bit. And ground-based telescope. So from those telescopes, we can get the mass, the radius, and the orbital element of all of those planets, which is quite nice. We can already learn a lot of things about it. So by detecting the planet, we also sort of characterize them a little bit. So I have this slide to show what radial velocity is. Someone want to explain what is happening here? Oh, it's too intense, isn't it? Okay, so I can explain it if you want. So there's, why is it shaking? Okay. There's a star in the center and the planet orbits. The planet influences the star via gravitational pull, and if you take a spectrum at very high resolution of the star, then the spectral lines of the star will shift a little bit by Doppler shifting. And this is basically a periodic event that you can characterize, and from there you can, if you know the mass of the star, you can determine what the mass of the planet is. So it provides the mass. It's a cool technique, but it's not perfect. It's biased towards massive planet because the more massive it is, the more it's going to influence that sort of wobble. And it's also very sensitive to close-in planet, but not planets that are far away from the star. It's usually done from the ground because you need quite high resolution to get those spectral lines. Then there is the transit. I don't know who told about the transit, I think. Yes, you did. So it's basically when the planet goes in front of the star, it gives the radius. There was a question in the quiz about the radius of the signal of a Jupiter-sized planet. Do you know how to get that information? Did someone find it? No, really? Okay. Well, I'll explain later, or you can find it. But it's quite easy, actually. If you think about it, the radius is giving you the area of the shadow. So you can just compute the area of the star and the area of the planet when it's eclipsing, so the shadow, and you can just do a normalized quantity to know how much it must decrease. The answer was about 1%, I think, for a Jupiter-sized planet around a Sun-like star. So we're looking at 1% variations in the stellar luminosity, basically. It's also biased towards large planets, not massive, but large planets, of course, and close-in planets. It's done from the ground and space. So what is cool, as I said before, is you can combine RV and transit to get information on mass and radius of those planets, which is starting to tell us something. So this is a small image of the Kepler Space Telescope that we just said it revolutionized the field. Why? Because detected about 4,800 planets. It was dedicated to just do that, to detect exoplanet via the transit method. It's about 1 meter size. And the primary mission finished in 2013 when 2 of the 4 reaction wheels broke. It's a cool anecdote. Do you know what they did after at NASA? Come on, surely someone knows. Because Kepler has been active to 2018. Sorry? Yes, so what is the principle of K2?
I don't know, but it's an extension of the instrument.
Yeah. So,
it's totally open to the community?
yes. But Kepler, so the end of the Kepler mission was when those 2 reaction wheels broke. Do you know what the reaction wheel they do? What they do? They allow to control the telescope in terms of like where it's pointing. So if you break 2 out of the 4, you only have 2 remaining reaction wheels, and you can only point in 2 axes. But you need 3 axes to be stable and be able to observe a target continuously, which is what you want for transit. So what do you think they did? It's not that obvious. It's a bit, I mean, I'm always amazed when I think about what they did at NASA. Okay, so they did this. They put in service K2, which was a second light, so they reborn Kepler, and they balanced the 3rd axis with the solar wind. So if you see here, we can't really see it in those pictures, but the solar panels are quite nicely angled, and they are symmetric. So they basically balanced the 3rd axis by just having the stellar, the sun pressure going exactly here at the center of the solar panel, which gives them the 3rd axis control. And so they did that, used the telescope for 4 more years and detected a massive number of exoplanets with this. The screen is not amazing, but Kepler was supposed to just observe this little patch of the sky, so it observed only here for the first part of the mission. And with K2, because you need to actually have the stellar wind with a specific angle, they were forced to sort of follow some specific pattern. So those are sectors. They basically shift the telescope by 90 degrees every time that the stellar pressure is not good enough. They shift by 80 degrees. So you have, I can't see the number, but I think you have 1, 2, 3, 4, must be here or something, 5, 6, and goes continuously with shifting by 90 degrees every time. Do you have any question, or do you want to interact? No question, you're sleeping. The crème anglaise was too much. Okay. Now this is the revolution. In 2018, NASA sent TESS, so the Transiting Exoplanet Survey Satellite, where the goal now is not to look at one specific patch of the sky, but to actually cover the whole sky and detect exoplanets for the entire sky. It's composed of 4 different small cameras, so it's much smaller than Kepler, so it doesn't have the sensitivity of Kepler, but it observed the whole sky, which is quite nice. There was a 2-year primary mission, and it's been extended for 2 more years because it's so successful, like finding candidates, and we now have around 5,000 planetary candidates. So if you add up what we know already, which is like 4,800, and you assume that most of them are actual planets, then it gives you an idea of the number of planets we actually have in our catalog at this point. Why are they candidates, do you know? Usually you have to observe another, like multiple transit events, but you also want to observe it with multiple techniques. So for example, you'll get radial velocity on top to verify that the mass is consistent with a planet, because you can have false signature. For example, stars they also have periodic events, or a brown dwarf could go around a star and it would technically create a signal that is pretty similar. So yeah, all of those candidates, they need follow-up observations to be confirmed, but it's likely that a significant fraction of them are actual planets. So I've put this video to show you, does it work? Yes. To show you the observing strategy of TESS. So this is Kepler, the field of Kepler, and this is one of the small camera. And you have 4 of them observing at the same time. This is a 1-month observation, so we stay for 1 month here. And you rotate every month until you've covered the whole sky. And in 2 years, you basically have covered everything. In the extended mission, they'll go back to the southern hemisphere and also this portion here, which has not been covered yet. It's only a 2-year mission. If you want to get a planet and be sure that this is a planet, you need at least 2 events, 2 transit events, or maybe you want a little bit more. So it tells you something about the period that the planet needs to have to be observed in a 2-year mission. Do you see what I mean? So if you, for example, with TESS, one of the big biases that we have is it's only observing for a month a portion of the sky, which means you can only get planets that have orbital period less than 15 days, for example. So with Kepler, the strategy was a bit different. Does that make sense? Yes? Good question, though. Other questions, comments? Someone expert on Kepler or TESS who wants to? Okay, so this is a TESS light curve of WST 62b. That's hot Jupiter, and you can see here the transit events that are happening very periodically. So from there, you can just fast forward the data or fit the whole light curve. There is a bunch of systematic you need to account for. It's likely to be the star or the instrument, and then you can get your parameters for the planet, which are usually the radius for transit. Gaia, so no one knows what Gaia does. It does star, right? This is written here. But thank you. Yes, this is exactly the objective. So, do you think we can use that to detect exoplanets? So we have basically, what was said is we have very accurate position, velocity through time of where the stars are going. What can we do with that? Almost. It's no radial velocity, because radial velocity by radial means it's in the radial direction that you're looking at the star wobbles, but you also look at the star wobbles, so it's good answer, partial answer. So yes, you know basically where the star is very precisely, and you will look at periodic movement of the star as compared to the sky background, and that would basically indicate that there is a planet that is sort of orbiting, and you can get information like the mass, the orbital period, things like that. It's quite interesting. Problem is the low sampling rate. It only observes a star for 15 times a year, which makes it very difficult to detect planets with this technique, or at least with Gaia. Plato. Okay. So the goal, it's a European Space Agency mission. It's not launched yet. It's 2026. The goal is to detect, in this case, rocky exoplanets around bright stars. So it's basically looking at Earth 2.0, or looking at planets that are that have the same characteristics as Earth. So it has a bunch of small camera, and this is going to be a 4-year mission. The goal is also to obtain very high precision on the radius of all of those planets detected, and that gives us density. When you combine with the mass, there is on top of getting the radius, they will follow up those observations with radial velocity, which will give very accurate radius and very accurate mass, and then we can make up the density of all the planets, again, in the Earth-size regime. So it is quite nice.
What is the precision you have on the radius?
3%. You can't read it. It's
No, but it's with Plato, no?
yes, with Plato.
And now, if you do
It's a good question. I don't know. I don't know, probably less, but I guess what's impressive is it's 3% for small rocky planet, right? And if you, I think I have a plot, a few slides after. Remind me to check whether there is any planet that look like Earth in this plot. Because in terms of detection, so far we've been very biased towards the big hot Jupiters, right? So with Kepler, we've also detected small, maybe super Earth-sized planets, but they are in a much closer orbit, so like with very short periods. So yeah, this is looking at a different population. Yes, any question? Oh, there are questions. It's
so
nice.
The goal is to detect rocky planets, but you deduce that it's a rocky planet only by the density of the planet, and it's complicated. Like if we have many combinations,
Yes.
to have the same density.
Excellent. Yes.
Okay.
So if you get mass and radius for the big one, it's actually easy because the big one have a low density. So you can say, okay, they are probably gaseous, but you probably know from the solar system it's difficult to say what the interior of those planets is, right? It could be like a core with some gaseous envelope. For the very small ones, you can always say they are rocky because when you have a density that is consistent with Earth, for example, it can't have a significant fraction of a gas envelope. So it can be rocky with a secondary atmosphere or just like a bare rock object like meteorites.
Okay, so they fix a threshold and said that potentially under this it's possibly.
Yes, and you have this region, so you know all of those planets we call sub-Neptune, super-Earth, all of that. We actually don't know what they are. We have no clue. They can be icy, rocky, with large gaseous envelope, just pure gas with just core of iron, and it's difficult to say. When we classify planets as being Earth-like, we mean they're roughly the size and the mass of Earth. I don't think people have used this term for meaning that they are like temperate, because in this case they would use temperate Earth-like planet or something like this. Yeah, but I totally disagree in general with the way people are naming planet into different categories, because it's very ambiguous in some cases. We find hot Jupiter around any type of star. They are rare, very rare in terms of frequency. When when you correct for all of the systematics, for all the detection biases, we actually can tell that they are rare, but we detect them primarily because they are big and they orbit with short orbital periods, so you have a lot of those events. Yeah, we detect any kind. We detect hot Jupiter, but also small planets in very close orbit. I'll talk about one of them, which is one of my favorite, a bit later. Other questions since we are here? It's absolutely okay if we don't go to the end of the slides, right? We can just stay on this slide forever, have this discussion, and I can finish anytime at dinner or something. I'm just going to move on a little bit and talk about the planets now. So hot Jupiter, I've chosen just one example. Why is it moving so much? I've chosen just one example per category because there are actually plenty. No, actually for hot Jupiter I have a few because those are my favorite, but my second favorite. Anyway, so I've chosen this one, HD209, because this is the first one that has been detected in 2000. I've put a number of references. This is not exhaustive. People for this planet, there are like thousands of papers, maybe not thousands, but this is just an idea. If you're really interested in one particular planet, just start looking at those papers and then you can move on to the other ones. But basically, this is a 1.38 Jupiter radius, a bit bigger than Jupiter, but it orbits in 3.5 days, which means it has a temperature of 1,500 Kelvin. And this was the first transiting exoplanet, so I put it here as a reference. Then KELT-9b is interesting because it's also a big one. It's 1.37 Earth radius, but if you look at the mass, this is really tiny, right? 0.2 times the mass of Jupiter. So it's what we call, The press calls that a superpuff, and it has a very, very low density. So it's very difficult to explain why those planets can exist, and I don't know. But anyway, it's also very hot. There are a few papers here if you're interested. KELT-9b, so we start having some animations. I like this one because it's the hottest exoplanet we know to date. It's about 4,000 Kelvin. It orbits a big A star, and it orbits very close, 1.5 days. It's not tidally distracted, but it's on the verge. It's very close. It's also interesting because it's evaporating. So in the animation, it's a NASA animation, but they make it look like a comet because it's actually evaporating a lot. And it's also in a misaligned orbit, as in the star you can see here is orbiting on the counter direction from, like at the 90-degree angle as compared to the orbit of the planet. So it's pretty interesting. How did this planet end up here, right? Any question or comment? Do you know why the planet ended up here? Because I don't. Okay. Then we have those sub-Neptune planets. So they're smaller than Neptune, bigger than Earth. This one has a 1.6 days orbit. It's called GJ1214. It was the first discovered in this class of object that we actually don't have in the solar system. We don't have planet between Earth and like Neptune, right? And those are the most abundant objects that we observe, actually. So it's a mystery. Why do we observe all of those objects, but we don't have any in the solar system, right? It's also interesting because the internal composition is totally unknown. It's in this regime where the mass and radius give you a density, but it's a little bit higher than just being full gaseous, full hydrogen, helium, but it's not quite rocky, so it's somewhere in the middle, and we don't know what the internal structure of those objects is. There was a spectrum. I don't know if you're familiar with spectra, but that basically means that we looked at the atmosphere of this planet, and it was like, oh, we can actually fit anything to the data points, right? It can be full solar composition or 100% water atmosphere or some mix with hydrogen and water. So it didn't tell us much more. What we think happened here is it's actually cloudy. So the clouds are sort of masking every atmospheric signatures that could be there, and we don't see anything. There is also like a literature that is massive on this object. Then Able planet, I don't really know why I put this one here because it's TRAPPIST-1F, but I'm talking about the TRAPPIST planets after. I guess it's interesting because all of the planets we are looking at the moment are tidally locked. So basically keep in mind when someone talks about a planet, it's likely to be tidally locked. So it has a very different condition on one side and the other side. There's a night and a day side. This one has temperature and is remarkably similar to Earth. So it's one that is going to be scrutinized by James Webb quite a lot. Yeah, those are some papers. There is also a HST observation of the atmosphere, which tells us that this doesn't have a hydrogen dominated envelope without clouds. Okay, doesn't tell us much more. But K2-18b, so I put it in water world, but honestly, sub-Neptune's water world, they are the same, and super Earth, they are also the same. We don't really know what they are, because again, they are in this density region where there is no real way to say what the internal composition is. This one made the news because the temperature is 270 Kelvin, which is quite temperate. And it's the most temperate planet for which water detection, the most temperate and the smallest planet for which detection of water has been done. So there is water in this planet. now we don't know how much. We don't know if this is a water world, if this is an hydrogen-dominated planet with some trace of water. It's impossible to say at this point. So again, this one's going to be observed a lot by James Webb. I put this graph here that provides some different composition, internal composition models. So if you follow the line, this is iron. So if the planet was 100% iron for a mass of 10, it would be here in terms of radius, right? And then there are different composition lines, so silicate, pure water, and then some mix of other things. The only important point to take out this graph is all the lines, they go here. The only thing we have for those planets, most of them, is just like how much light is decreased in the stars. So we don't do mapping of those things, right? What do you want to know about able planets? It was suggested that if this planet had an ocean, it would have to have one side which is warm enough for it to be in the liquid form. But on the night side, it wouldn't be this temperature, right? It would be like something like minus something, so it would have to be icy. But it doesn't mean that this planet looked like that, right? I just put it here to discuss tidally locked planet, right? Does that make sense? Yes? Cool, any other question? Any comment? Do you know more planets? Because there are a lot more. So you were talking about lava planets. 55 Cancri is one of them. It's a little bit larger than Earth, but it orbits in 0.7 days. So it has temperature of 2,500 Kelvin. Sorry. What I like about this planet is, on one side, the temperatures are high enough to sort of vaporize all of the rocky surface. So you would have something like a lava ocean, and some of that vapor would contaminate the atmosphere. So if you were able to observe the atmosphere of this kind of planet, you would technically find some rocky element like, I don't know, titanium or sodium, things like that, which would help you to eventually link to the internal structure of the planet and maybe how it formed or something like that. And there is actually observation of this planet for the atmosphere, and HCN was detected. Okay, but another paper say that actually there is no atmosphere on this planet. So who knows? So now the TRAPPIST system, so this is a pretty cool system. I have a nice video here that I'm going to let you enjoy, and it basically presents a artist impression of what all the planets are here. And then I'll tell you how those artist impressions have been done. I'll show you what the data looks like. So I think this is D, so this one. E maybe. You'll recognize the Able planet, F. And all of those planets, so they orbit an M dwarf, which means the energy output of the star is very small, but they orbit from very close in hot regions to temperate regions to very cold regions. But this whole system fits here, like here, in the solar system. So Mercury, I don't know if you can see in those slides, but Mercury is here. It's just like a mini multi-planetary system. So do you want to see the data? You don't have the choice. I'm controlling the slides, right? So that's the data. We know all of this. We've done all of those artist impressions based on that, right? So planets are cool, but yeah, it's a bit, there is a lot of interpretation when we see those things. We of course have models and so on, but keep in mind that we actually don't know a lot about those planets yet, especially the small ones, because they are difficult to observe. Oops, sorry. Yeah, so they had to, because the system has a lot of planets, they had to decorrelate this very complicated light curve. So you have to actually model the whole system, and there's a lot of interesting orbital dynamics that happens here. So it's quite nice. Question, comments, TRAPPIST experts. Did you get the question right when I said, what is TRAPPIST in the questionnaire? So, excellent. Didn't get tricked. It's nice. Okay, so basically, so I've shown you a few examples just to expand a little bit now. So basically, we have all of those classes, but there are even more diversity in exoplanets, right? So exoplanets are very diverse. It's like fiction, basically. You can take any planet from any of the space movie, and I'm sure that exists, basically. They are also ubiquitous. Okay, so that's the graph where I needed to see, okay, okay, see? So that's where Earth would be. And we don't detect any planet here. It's not because there are no planets here, it's because our detection techniques are limited, right? So Kepler, sorry, not Kepler, Plato, technically will help us fill this gap here, right? I think all of those planets are detected via radio velocity, so all of those big ones, but quite far away because the semi-major axis is too large, so they have a long orbital period. They are too large, too far away to be picked up easily by Kepler or TESS. And all of those here on this side here are transiting planets. Maybe not all of them, but.
Do we have enough precedent to know if a planet has a moon?
Good question. There was one candidate, I think. You can type, it's David Kipping and Alex Tichy. So they observe a sort of like a double transit multiple times with Kepler on one system. And they followed up with HST and said, okay, it's also in the HST data, so it's consistent with the moon. They ran a significant amount of model, but I think it stayed at the candidate level, basically. There is no confirmation of it. I think F is very similar to Earth in terms of equilibrium temperature and size, I think. So that's why people are going crazy for those. So for F, it's located where there is exactly just the right amount of light, right? But we don't know if it has an atmosphere, nor if it has water, because we don't know where this planet formed, how it formed. If the star was active, a lot of UV, you can evaporate a lot of the atmosphere. So maybe it doesn't have an atmosphere. But I think models suggest that they are likely to have atmospheres. But we don't know from observations, and I tend to be convinced by observations more. Any other question on those planets? It's too bad that we don't have a TRAPPIST expert. Okay, so all of that I think we saw. This is okay. Yeah, so the other point I wanted to make in this slide is, so that's the frequency of planets and sort of their class, or if you want, their size. So you can see actually the gas giant, the large planet, are quite rare. Even the hot Jupiters, they are quite rare, even though we detect a lot of them. But the planets that are the most common are those class, so the super Earth and the mini Neptunes, and we have no clue what they are made of, right? So on top of being very diverse, exoplanets are also ubiquitous. Well, I guess Jupiters, they are just the planets that have the size of Jupiter and that are very hot, right? They have temperature, I don't know, hot could be something around more than 1,000 Kelvin. Under 1,000 Kelvin, you'll be more in the warm. People would tend to call that warm, I think. But then the classes are a bit, the boundaries, they are not well known, right? It's a continuous, or at least it looks like this is continuous. There is some occasion where it doesn't look like this is continuous, and this is subject to a lot of debate. And this is why some people are calling super-Earth, and super-Earth, sub-Neptune, because they fall in the same regime, but they are sort of coming from two different populations. It looks like. So I'm going to show that now, basically. So the same plot I had just before that shows the number of exoplanets, so the frequency of the different type of planet as a function of planet size. Again, the large planets, they are here, so the Jupiter-sized planet or hot Jupiter, Saturn planet, they are here. But we find that most of the planets, they are in this regime, which is larger than Earth, but smaller than Neptune, right? So we don't have them in the solar system, we don't know how they are. And on top of it, if you have enough granularity to sort of make those frequency precise, you can see that they are coming in two different population, a bimodal distribution, basically. So people have started calling this region super-Earth and this region sub-Neptune. But really, we don't know if they look like Neptune or if they look like Earth, basically. And on top of it, this is just, for most of them, the only information we have is radius and mass. So from radius and mass, you have density. So I like to call them transitional words, because then it's not ambiguous, it's transitional. We don't know if the transition is smooth or if it's sharp, basically, if they go from there to there in a very sharp way, or if there are a lot here, and this is just our precision, which is not good enough to see the transition. So on top of it, for those planets with mass and radius only, this is degenerate. We don't know what the interior is. So they could be something like this with a iron core, rocky mantle, and some hydrogen envelope, but they could equally have a layer of water, a little bit in between, and a hydrogen envelope, or they could just be pure balls of water. For all we know, with mass and radius, we can do all of those three solutions, right? On top of it, those solutions, they depend a lot on the equations of state that we use, and we don't quite know all of the information for those objects. So to me, it's very difficult to actually tell what they are. One way, and this is one of my motivation to do atmosphere, is to observe the atmosphere, because then you get an additional constraint to your system. If you can tell, okay, actually the atmosphere is water rich, then it tells you something maybe. Or if it's hydrogen rich and very dry, it tells you something else. So there is this question that I think is fundamental, and James Webb is going to help us to solve that. So what are exoplanets made of? Also, how do planets form and evolve? I like to say that we have ALMA observation of disks. This is nice. This is our initial condition. We have disks, right? And planets form in there. But essentially, the exoplanets at the end, they are the outcome of planetary formation, right? So you have an image of the initial picture and the final picture, but this path between here and here is not yet completely understood, and this is true also here in the solar system, right? So by looking at exoplanet more and atmosphere, we can hopefully constrain planetary formation models and understand a little bit more all of those systems evolve, dueling between atmospheres and planetary formation mechanisms. And then again, a last motivation, which I really like. I don't know anything about the solar system, but I do like to think that the solar system is just one outcome of planetary formation, right? It's just one scenario we have. We can study it a lot by doing in situ measurements and stuff, but it's only going to tell us something up to a point, right? To understand the fundamental mechanisms that are behind planetary formation, we likely want to see more outcomes of this right? And by looking at planetary system and stuff, we can get more outcome of planetary formation and eventually feed it back to solar system science, right? For example, you probably know more than me, but do we know why water is on Earth? I take that as a no. Do we know why we have two gas giant planets and they are far away? Do we know why we don't have super Earth and sub-Neptunes or sub-Neptune, transitional worlds? Okay. So yeah, I think those questions are quite essential to answer, even if we want to understand the solar system. So it's putting, sorry, it's going too far. It's putting the solar system in a galactic context, basically. Okay. Any question on this part? This was only about detection and only by having mass and radius as constraints. The first measurement that you can do if you know how far the exoplanet is from the star is to do a rough calculation of the equilibrium temperature, right? This is what they state in a lot of papers. However, you know from the solar system it's not an accurate measurement. So you can observe atmospheres and get information about the temperature from the atmosphere as well, which I think is a different kind. It's a different information, right? So I'm going to move on a little bit to the characterization of exoplanets then. So there are three main techniques. So far we've talked about transit and radial velocity, a little bit about direct imaging and so on, but for atmospheres, people have actually looked at other techniques as well. So you have a planet orbiting here. It can take a big space telescope and look at the transit, of course, which is quite nice, get a lot of information. But you can also look at the day side of the planet by looking at the eclipse, right? Because remember, those planets are tidally locked. They have a night side, a day side, right? So when it goes in transit, you're looking at the terminator region, right? When you're looking at the eclipse, you're basically probing the day side of the planet, right? Some people also have analyzed the whole, it's coming, yeah. The whole information. So if you have enough telescope time to observe a planet for 2 days, then you can constrain the entire phase curve, which is quite nice. Okay. No, I should talk about CHEOPS, which is a space telescope that has been launched in 2019. It's led by the European Space Agency. And the goal is to determine the size of known exoplanets. So it's only doing characterization. It's not looking at detecting planets. It's characterizing planets that are already known. It conducts in-depth observation of known exoplanets. And I think someone in this class is more expert than me on CHEOPS. So if she wants to discuss this, she can take the lead. I've just added a few examples of observations that have been done with CHEOPS, which I find particularly interesting. There is this planet, WASP 189b. So it's a hot Jupiter. It's a very hot planet, and it orbits a star that is a fast rotator. So the star is actually not spherical. It's a bit of a potato-shaped star. And with CHEOPS, so this is the observation from CHEOPS here, you can fit the light curve that has been observed there, and from this light curve you can see that depending on the model you use, you get different type of systematics, like of residuals. And the model that is used here, so I think this is, which one is this one? Well, the nice one, basically, the one that has GED, so it's called gravity darkening, is because the star, by being a potato shape, has a different darkening depending on the direction you look at the star, like radially. So by looking at this effect and by correcting these residuals, you can actually figure out what is exactly the orbit of the planet around these stars. I found that quite fascinating and quite interesting. Yeah. There's also this nice system, TOI-178, which has been observed by CHEOPS. It's a pretty nice system with a lot of resonances. That's a GIF I found on Google that shows the orbit of all of the different planets, and they are all in resonance. It's quite, I mean, not all, I think 5 are in resonance out of the 6 planets. We know also that the 4 outer planets are gaseous and the 2 inner ones are rocky. It's quite a nice system. It's a bit similar to the TRAPPIST system, if you want. Also put the observations from CHEOPS just to show you how messy this is. So it's transiting all the time, basically, and you have like multiple transits at the same time. So the moon observation, the observation from Kepler to detect the moon, I think someone asked a question about the moon, was based on similar shapes. Basically, you have the initial transit, and then you have an additional just after that comes and was deemed as being a good candidate for the moons. Okay, so that's TOI-178. Do you have any other question on this part, or any comment, any other CHEOPS anecdote? No? So you're talking about stellar activity, like stellar spots, faculae, things like that. Yeah, it's very annoying, because, yeah, this is annoying, especially for atmospheres. I think for detection, we can pretty much rule it out. After some observation, a significant number of observations, you can rule out a false detection as being stellar spot quite easily. But for the atmospheres, it actually creates signal that can mimic atmospheric signals, like, for example, Rayleigh scattering and things like that. So it's a little bit annoying for stars that are active. Most people just like avoid to talk about it, basically. Okay, so Hubble is still the state of the art for exoplanet atmospheric characterization. It was sent in 1990, and it was not aimed at doing atmospheres, right? Because remember, back in the day, we didn't know about exoplanets. In fact, we discovered exoplanet after, right? So it's a general purpose observatory that was repurposed to do atmospheric studies. It's 2.4 meter in diameter, which means it's quite large. And it will end in 2030, 2040, hopefully. We can use it for a bit longer. It was serviced 5 times in space by the NASA with the space shuttle back in the day, and the JWST camera, which is what is used for exoplanetary characterization most of the time now, was installed only in 2009, right? So I have this image, which is quite interesting, of Hubble of the same galaxy at 3 different times, right? This was the image from 1993, when basically, let's put it this way, they didn't make the Hubble mirror quite in the right way, so there was a lot of spherical aberration in the primary mirror, and this is what an image of a galaxy was looking like. So quite embarrassing. It was actually built, the mirror, I think the fault was on a contractor from NASA. So we skewed the telescope by sending a space shuttle to sort of install lenses that comes in between the mirror and the end of the telescope to sort of correct for the spherical aberration of the mirror. So it's like they installed glasses on James Webb, on Hubble, basically. So the instrument that is correcting for that aberration is called COSTAR. And that's the JWST camera image of the same object, so that galaxy Messier 100, which taken in 2018. Okay, How do we observe atmospheres? Do you know? Spectrum, I heard. Someone wants to explain? I actually have all of the three here. Just to give you a small idea, and we can redo our actually you're gonna redo the calculation of the size of a signal by a Jupiter-sized planet around a Sun-like star. What's the radius of Jupiter as compared to the Sun? 10%? Yes. So because we're talking about surfaces, are you Googling it?
No. I said 1.
1%, oops, sorry. 1% is the size of the signal, but it's because the radius is 10% smaller. So if you do the power 2, then you get 1%. But yeah, if you only have 1%, you just have to do pi L squared divided by pi L square of the star, and this is what you get, right? You can do it with eclipse as well. So this is the out of eclipse, and this is the eclipse. So you're going to look at the differential signal, and what you find at the end is you have something like surface emission multiplied by the radius square. Sorry, the square is not on BP. It's a mistake, right? It's just B is alone, right? Same for the star, and then you can get the signal. And actually, the signal in emission is about 10%. The signal for hot Jupiter this time is about 10% the signal of that you get in transit. So it's even a more difficult measurement. For the atmosphere, well, if you in the first approximation, you can just take this formula and add plus h for the size of the atmosphere, which gives you this. Then you can just say, okay, actually h will be wavelength dependent because it only absorbs at the wavelengths where you have a molecule to absorb, right? And this way you can create a spectrum and start your analysis from there. Yeah, okay, this is what I explained, very crude. There is also some way via the STScI to know what the size of the atmosphere is, what is the size that you can expect. The cool thing about transit spectroscopy is it's very sensitive to the mean temperature, so the scale height of your atmosphere. So there was the question about the temperature, you can get it from the scale height. It's also sensitive to clouds, so if it's cloudy, it's going to be fully flat. You don't see any spectral features because they're basically covering everything, and also to molecules. So it's quite nice to use transit for atmospheric characterization. So I've run a few models here to show you basically the impact of the different parameters on a spectrum. This is a typical hot Jupiter planet, and this is the transit depth. So that quantity here as a function of wavelength, and you have different temperatures. So you can see if I drop the temperature, let's say from the blue one, which is 12,000, to the red one, well, the size of the feature, which is basically this, they are going to decrease, and it's going to be more difficult to observe this kind of, this one's going to be more difficult than this one. Then if you add clouds, so for example, you will go from this one to this one, you're masking some of the features, and it becomes difficult again to observe the atmosphere. Then also the abundance of your element is important. The more you have, up to a certain degree, because after up to a certain degree, the more you have, the more you absorb, and the more signature you have. So it's what I was showing here between the green and the red. For the secondary atmosphere, so the ones that are heavy, you're actually going to impact this mu, which is the mean molecular weight. And if you see what this is underneath. So higher mean molecular weight means that you're decreasing the size of the atmosphere, and then you don't see anything anymore, which is why the TRAPPIST planets are difficult to observe for their atmospheres, for example. Is there any question on that? This is all the math you're going to get today. Not really math, right? Questions? No? So transits have also been done for Venus. So you can see here the thin atmosphere. So this is basically that thin, I mean in this screen we don't see it, but it's that thin signal that we are trying to extract, right? Now just to go on other difficulties you have with HST. HST, because it was not built to do atmospheres, it's a bit too sensitive for 10 minutes. Wow, okay. It's fine. It's a bit too sensitive for the type of star that we observe, so the bright star, and you basically have to scan the signal on the detector. So basically the telescope just does up and down to not saturate the detector. And that's a spectrum of a real planet here. So there is a very complicated pipeline that I don't have time to go on for now, but basically you need to extract this signal here, which is spread across the detector. It creates uncorrected light curves, which are very complicated because they have ramps. Those are systematics that are characteristic of HST, so those ones, and there is also like long-term ramps. Then you can do this job, correct for the light curves, and also do that as a function of wavelength, so you get a light curve per wavelength that you're interested in, and from there you can build a spectrum. And from the spectrum, you can figure out what was absorbing in the atmospheres. So I have a few examples there. Do you know what this thing is here, like everywhere? It's written in the slides. It's water. So for all of those planets, all of those are Jupiter, we most of the time find water. Why? Because HST is sensitive to water due to the wavelength coverage from 1.1 to 1.6 micron. The main absorption we have there is water. There's a bunch of other absorption here, like TiO, VO, and FEH, that, and NH3, that I'm sort of highlighting there. There's also carbon-bearing species maybe here, but it's much more tentative, and it's quite debated whether those molecules are actually there or not, or if they are just fluctuations from statistical, from just like the systematics of the instrument. Okay, and that's an example of a small planet, and you can see here it's basically very flat, so we don't actually see any evidence for molecules in those because the scale height of the atmosphere is too small, maybe. So I was going to go into atmospheric retrieval techniques, but we're going to skip that just to say that this is a very complicated problem because we are in a low signal to noise regime, and we absolutely want to know what is the significance of our detection, right? So there is a bunch of statistical techniques that are developed to know that and to explore the parameter space to find all of the possible solutions for a spectrum. So I'm just skipping this. Okay, I can get pretty interesting. So there was a few studies that have been looking at the planet not as single object, but as populations, like those three. For example, in this one, there was 30 planets analyzed at the same time, and you can recognize here at 1.4 micron that most of them have water. So all of that to say that those studies, they have basically paved the knowledge of exoplanet by telling us most of the hot Jupiter, they get a lot of water and are also cloudy. To me, this is what is the most interesting, like looking at the populations instead of a single planet. There's also some speculation on refractory elements, which might come with a trend or not. Then Spitzer. So I was going to talk about emission for Spitzer because you can Spitzer looks a bit more in the infrared, so it's looking at 4.5 and 3.6 and 4.5 microns instead of 1.1 to 1.6. which means the planets, which are much cooler, emit more at those wavelengths. So you can actually see the eclipse, so the occultation also called, much better with Spitzer. Do you have any question on all of those parts? You all want to go for coffee? Okay, then I'll skip that. I was going to ask you, do you know what this means? So this is a spectrum in eclipse. So you see the emission of the planet increases, and there is a spectral signature here, right? And there is 2 Spitzer points here. Do you know what this tells us? So this tells us that the atmosphere has water vapor. This is absorption from water, right? And because this is absorption, the thermal profile is going to go by decreasing with altitude. If you had the opposite, so like a increasing emission, then it means the temperature profile go with increasing with altitude, which is quite interesting. So from eclipse as compared to transit, you can also get some information about the thermal structure, which is quite nice. Okay, next decade of exoplanet survey. It's just HST wavelength range. Takeaway is very limited. This is Ariel, right? So large coverage, and this is James Webb, so pretty cool. The more we have coverage, the more we're probing different altitudes and the more molecules we can get. So with exoplanet, signal to noise is important, but also wavelength coverage. So Ariel and James Webb are going to be amazing for that. Okay, this is an example. Do you know how to read those graphs? No, okay. Posterior distributions, do you know? Okay, so we're not going to talk about it then. Just going to show you 2 videos then, and we're going to stop there to go for coffee, if you want the rest of the presentation. This is just to show you how crazy the deployment of James Webb was. Just to give an idea, so this is the size of a tennis court, which is quite impressive. Do you have any question while we are watching the video?
Is it finished?
What?
The sequence of...
I don't think so. I think they are at the time where they are aligning the mirrors, so it's almost completed. But most of the single point of failure, because there was a few, were happening in this sequence where they opened the sun shield and opened the mirrors. So we're past that sequence, which means we're technically safer. I call it, it's a general purpose observatory. It was initially designed not to do exoplanet either. So it's doing cosmology, a lot of galaxy. It's looking at the first galaxy in the universe, things like this. This is just to show you the difference in terms of spectra that we have. This is the sub-Neptune K218b that I was talking about earlier. Sub-Neptune or water world, it depends on how you want to interpret it, of course. But there is a water signature at 1.4 microns. And this is what the observation from James Webb is going to look like. They are the same models, so there are 3 scenarios. They all look the same in HST, but they are very different in James Webb, which is quite nice. So we're going to be able to break basically all of those degeneracies with James Webb. Posteriors, some of the planets. I also wanted to touch a little bit upon 3-dimensional aspects really quickly. So I don't know if it's going to start. No, it doesn't. I just started here. Up. So those are dynamics simulations in 3D of what hot Jupiter should look like. And you can see it's very, very dynamic. So to me, all of this complexity is going to be super, super interesting, because with James Webb, we're going to be able to observe those things, right? So all of this temporal variations, basically. So you have storms and jets and things like that, which are predicted on exoplanet and should be observable with James Webb. So the way you would do it is maybe to do it with phase curve, which allows you to map the atmosphere of the planet. So you look at the planet when it goes around the star for a full orbit, and if you do that in spectroscopy, then you can sort of infer the thermal structure and the partition of the molecule in the atmospheres, but in 3D, not just at the terminator or at the day side. Yeah, and I'm going to stop after this slide, which is on Ariel. So Ariel is going to be launched in 2029. That's another telescope, smaller than James Webb, but as opposed to James Webb, it's going to be dedicated to exoplanets. So it's only going to do exoplanet atmospheres. It's going to be the first mission to do that. It's 1 meter size. And in its lifetime, it should observe around 1,000 exoplanet atmospheres. So it's quite a lot, and from there you can basically build your population and do the same figures that we've been able to do with Kepler, but with the information from the atmosphere. So hopefully break all of the degeneracy about the small planets, and also understand the chemistry, the structure of the cloud, link the chemistry to the planetary formation, all of those things. And I'm just going to stop here because I don't have more time, and I'm going to move directly to this slide, which is my conclusion slide of all the telescopes that can be used from space to detect or characterize exoplanets. And this is the final slide. Yeah.